Let us learn the concept of how do you create factors of expressions, okay? So let us go back a little bit and see what we remember about factorization. If I take a number 42 such that I want to divide this number into its individual prime factors, I always start with 2, the lowest prime factor, and divide a number and see if it is divisible, right? 42 is divisible, I get 21. 21 can be further divided into 2 prime factors, 3 and 7, and we are done. So, in essence, what you're saying is 42 can be written as a product of 2 times 3 times 7. Each term is irreducible because each one of them is a prime factor, right? The same concept is applied in expressions. So, if I take a simple example, 6x cube, a monomial expression, and I say that I want to divide this expression into its individual components so that each term becomes further irreducible. Then I say that, well, 6 can be divided as a product of 2 prime factors, 2 and 3, and x cube can be written as a product of 3x. Now, each term inside this expression is irreducible. So this is called factorization of my expression 1 here, okay? Now, this was extremely simple to follow, right? Let's say we have a binomial, okay? In this case, the binomial expression is 6xy plus 2x cube. Okay, now you want to divide this entire expression into its individual factors. So the technique is still the same, what we have learned right here or right in this example. You look at each term and see how you can divide each term into its individual factors. So 6 can be divided as 2 times 3 and x and y can be written as it is. And the second term can be written as 2 times x times x times x, product of 3 x's, right? Now, the next part is whatever is common in this entire expression, you take that out, apply the reverse distributive principle, and let the remainder stay inside the parentheses, okay? So I see that there is a 2 and then there is a x that is common across this entire expression, right? So I write 2x outside the parentheses, and what remains inside the parentheses is all the terms that had not been utilized. So 3 and y from part 1, and 2 is gone, x is gone, x and x. It remains x square inside the parenthesis. So now this is my factorization because this cannot be reduced any further, and this expression, the 3y plus x square, it cannot be reduced any further because each one of the term has nothing common between them. Okay, so these are my factors of the expression that we have here as example number 2. Now these of course were very simple. Let's take a slightly complicated example to understand the concept of factorization. So the expression I have is 6p cube minus 14p to the power 4 plus 2p to the power 5, okay? And let's divide this entire expression into its individual factors. Now you need to make some observation before you start exploding this entire expression into its components, okay? What you need to do is find out what could be common across each term inside this expression. You see that there is a 6, 14 and 2. Each one of those could be divided by 2, right? And then there is a p cube, p to the power 4, p to the power 5. Each one of those could also have p cube as a common factor across each term inside this, right? So let us break down each term into its possible factors, right? So it is 2, 3 and then there is a p cube. Minus 14 can be written as 2 times 7 and p to the power 4 can be written as p cube and a p, right? And the last term can be written as 2 as it is. P to the power 5 can be written as p cube and p square. You notice that even though I have written here as a product, but when you multiply these two things, you get p to the power 5. So we can do that, right? That's how you actually find the factors. Okay, now look for what is common across each term. There is a 2 and p cube. That is common everywhere, right? So what we do is we write 2p cube as one factor that is common across everywhere, and then by applying the reverse distributive law for this term, we then write inside the parentheses whatever remains once you take this common factor out, okay? So in the first part, only 3 remains inside, right? So let me write 3 here. In the second part, I get 7 and I get p. That is the only remainder inside it, right? So it is minus 7p. And in the last section, 2 and p cube are already gone. What remains is p square. So I will say that the expression that we had here has two parts. Part 1 is 2p cube and the part 2 is, or the expression 2 is what we have written here, p square minus 7p plus 3. Let's take one more example. So our example is x square plus 6x plus 8. X is a variable and of course you know that 6 and 8 are constants. So now let us observe this expression and see that the term 1 and 2, they have x common, but the term 2 and term 3, they have something else common. They have only a number 2 common. So there is nothing universally common across each term inside this expression, okay? But you have to be a little bit creative here. So this 6, that can be broken down into two parts, such as 2 and 4. The sum of these two numbers gives you 6, but the product of these two numbers gives you 8. So that means if I play with this middle term right here, I can create some common parts between these three terms. Okay, so let's see how we do it. Now I can rewrite my expression 1 here using this kind of concept. So x square can be written as x times x. 6x can be written as 4x plus 2x, right? We just divided this 6 into two pieces, 4 and 2, right? And 8 is as it is. Now I can take something common out of the first part, the x square and 4x, and that can be written as x times x plus 4, right? I am just applying the distributive law on this one side here, okay? In the second part, which is 2x plus 8, this can be also written as plus 2 goes outside the parenthesis and what remains inside the parenthesis is x plus 4. Now you see that I have this factor x plus 4 that is common between these two products, right? So if we do this reverse distributive law one more time, you could rewrite this expression such as x plus 4 goes outside the parenthesis, this entire expression, right? And what remains inside the parenthesis is x from the term 1, right? And 2 from here. Okay, now you have two parts where part 1 is x plus 4 and part 2 is x plus 2. Or in other words, you have divided this expression 1 into its equivalent expression that can be written as a product of two expressions. You could say that x square plus 6x plus 8 is equal to x plus 4 times x plus 2. When you open the parentheses, you will find exactly this expression. And this is the concept and this is the method of how you create factorization of expressions. We will continue with this journey in our next tutorial where we will learn about factorization of expressions using standard identity.